Psychological research plan to study the relationship between sleep and clinical depression, specifically wondering if less sleep can be associated with higher levels of clinical depression. All right, so the null hypothesis, here let's just do this. Let's call sleep level, we'll call as X, and clinical depression, we'll call Y. And so H naught is that there is not a correlation between the two. How do you like that for the null hypothesis? Makes it a lot shorter. And the alternative would be, let's read this again. Research plan to study the relationship between sleep and clinical depression, specifically less sleep could lead to higher depression. So you have a higher amount of depression if you have less sleep. Okay? Okay, so this is one-tailed or two-tailed. This is going to be one tail. And a few things that go with this. We're looking at them saying less sleep leads to higher depression. Okay, something like that. If they just said something like sleep level changes the level of depression, so we don't know if it's higher or lower, then that would be a two-tail. And then number 3, using the one-tail test for number 1, we set the alpha of 0.08. And the alpha is the same as the p-value, right? Okay. So this means we have a 92%. What's the word I want to use? What's the word I want to use? Oh my gosh, I lost the word. I'm sorry. Oh, we have a 92% confidence that we would find something in this kind of situation. Okay? So that's basically what we're looking at, because 92% plus 8% is 100%. All right? And then number 4, they say we have a p-value which is equal to 0.042 and set the alpha to 0.08. Okay, so this p-value, this is less than our original 0.05. So this would mean that we have a p-value less than 0.05, so we reject the null. With evidence supporting our alternative. Okay, so then what does the 0.08 alpha mean? Okay, so if we go back and look at what the notes were yesterday, so if we select the alpha, okay. So as we have stated, the basic rule of thumb is commonly applied research studies that p-values below 0.05 will allow us to reject the null hypothesis. This rule of thumb is common in both medicine and psychology, but it should not be the default choice. In truth, the researcher selects the level at which we reject the null. This level is called the alpha. Okay, so they are saying this. They're saying a 0.08. So originally, if they said, hey, we have a p-value of this, but now we are saying that we have an alpha of 0.08, this is, so being that 0.08 is a greater value than 0.05, this seems to find evidence to make it not as sure of that we're rejecting null. So evidence to fail to reject null. Okay, so it's kind of a little different perspective on it. Fail to reject. So our p-value is saying, hey, let's reject the null. This 0.08 is saying we have evidence to fail to reject the null. So this is going to lead us into our type 1 and type 2 tests. Sure. All right, so 4, 5. Which error is plausible in this scenario? Okay. So remember our table. We had this being true, this being false, accept this, and reject this. So they had kind of done this grid here in this fashion. So this was correct. This is a type 1 where we have an alpha error. And then this would have been type 2. So this is a beta error. We're not going to really focus on beta errors. And then correct decision. Okay. So let's look back at what we had said originally on this problem. We said we reject the null. So we reject the null. So this is a reject the null right here. So then we're going to reject this. So we've made the correct decision based on our information, which seems a little goofy. The consequence of making this type of error, I think they were trying to lead us to a type 1 error. I don't think we have a type 1 error. We have a type 1 error if you look at what we're saying here. Our p-value will reject the null, evidence to fail to reject the null. So is the null true? And we say false. Oh, wait. I just said that backwards. I'm sorry. Is the null true when we said false? Okay, is the null true? And this one we said we rejected the null. We reject the null when it's false. So let me see if that's it. Just say reject the null false. Oh, we have a type 2 error. I'm sorry. So we were rejecting the null when we actually said the type 2 error took place. So the type 2 error is basically just says, hey, and I'll just read what we had said. Type 2 error, when we fail to reject the null, that is really false. Okay? Did I do that right? We reject, oh, wait. What did I said? We reject the null. Oh, God, man, I tell you, this day's got to start all over for me. We reject the null. It's false. And we accept. No, it is a type 2 error. Jeez, I got to quit questioning myself. Sorry. All right. Alpha was set to 0.08. What would be the advantage to setting a lower value? Okay, so they said that alpha we had set to 0.08. So this would mean that we are 92% confident. Okay, if we made this lower, so if we said it was 0.05, that would be a 95% confidence interval. If we said it was 0.01, that's a 99% confidence interval. Remember we said the wider the confidence interval gets, the bigger the confidence interval, the more broad you are on the normal distribution curve. Okay, so your tails become really, really small, which, if someone says, hey, I'm 99% confident that something falls in here, it's such a broad part of your characteristics that you're looking at. So you just got to be careful with that. 7, alpha was set to 0.08. What would be the advantage to setting it higher? So if I were to set alpha, it was at 0.08. if alpha was higher, we lower our confidence interval to try and capture the parameter. Okay, remember that the alpha and the oh, never mind. Hold my tongue on that. All right, then on the page 102, it says a soda drink company is changing the taste of one of its products and wants to conduct taste tests to see which tastes better to their customers, the old soda flavor or the new. Coca-Cola did that. They came out with the new Coke and it bombed. People were like, dude, we want the original. But they did that to something called, it used to be called the Pepsi Challenge. Pepsi Challenge, they had in front of grocery stores, they would have different grocery stores, they would have a guy out there who was taking surveys, and they poured you a cup of Pepsi and a cup of Coke, and you had to taste both and say which one you liked better. But you couldn't see which one you were drinking because they both had the same color, and they would sit there and do it. But Pepsi kind of cheated in the whole thing because Pepsi was served cold and Coke was served warm.
Wasn't that new Coke thing just all marketing?
It was marketing.
That loss, brought it back.
Yeah, they brought it back, and they came back better than ever, and Pepsi then dropped again. So, but the Pepsi Challenge, what they basically did, I mean, I kid you not, it was, you know, you're walking into the store, you're like, oh, and there had this other guy saying, do you want Coke or Pepsi? And they had this cardboard box. It was yellow, and in front of each one was a cup of one of the sodas. And this one was warm, and this one was cold, and the Pepsi was always cold. And they would have cameras there at certain locations because they realized they were leading their population to say, you know, you're and they did it during the summer. So what do you want during the summer? You want something cool to drink. Oh, the Pepsi. Oh, I like this one better. And then they pull up the thing and said, oh, you like Pepsi better. They'd mark it down. Look, these people like Pepsi better. But it was all rigged. But it was kind of funny. But Coke reacted to it. All right, so state the null hypothesis and the alternative. So new flavor and old flavor, we'll call X and Y. So create our null that there's no difference in taste or difference in taste. And then we want the new to taste better than the old. Okay? Or let's change this. Let's see. Soda company wants a choice of new tests which taste better to their customers. So this one I'd actually say is equal. And let's say the new tastes better than the old. I'd say we could go with a one tail in this situation. They're saying it's a two tail. It says explain why this is a two-tailed test. Soda company is changing the taste of one of its products and wants to conduct a taste test to see which tastes better to their customers, the old or the new. I don't think it's a two-tailed test. I mean, you have somebody said, someone's going to come out, drink cup A, drink cup B, say they like A, next person does the same thing, says they like B, keeps going, A and B, back and forth, back and forth. I don't think it'd be a two-tailed test. You're trying to get something that has a better taste than the other. So, assume the study is considered statistically significant at 0.1 level. So number 10, I think it's a one-tail test. So I don't think that they were trying to lead you on that one. And then problem number 11, we set this at 0.10 as our significance. What does this mean? This means that we are 90% certain of our data, showing one way or the other. What is a plausible value of P? Okay, so if I would say that our P is probably going to be less than 0.05 in this situation when we're looking at it. And then what is the probability we make a type 1 error in this? So this is going to point to our type 1 error. So our type 1 error is 0.10 or a 10% chance. And remember the type 1 error, change, not that's chance. Remember a type 1 error is we reject the null when it's really true. Okay? And then explain the consequence of making each type of error. Well, I'm not a big fan of this, so I'm going to move off this. I don't like this. I like the Coke or the soda challenge, but I don't like how they're phrased and stuff. So we're going to go to 6-6. I am going to be on page 35. I can start taking my time. There. There. I think I'm good. Like this. All right. For those of you that are going to just stay on your phone for the rest of the year and not even have your book out, it's not going to hold well with me. I know I've been very laxed on it, but if you want to be on your phone, that's one thing. If you want to be on your phone and not have anything else on your desk, I'm going to ask you to leave. I mean, I'm sorry. You know better. It's disrespectful to me to not just have your phone exclusively out like, oh, I'm going to do whatever I want. It's not it. I don't like it. And I just kindly ask you, please, if you're going to have your phone out, you're going to be on your phone, please at least have your information out as well, what we're working on. And I know you're seniors, and I love you to death. You know that. But I'm just kindly trying to ask you to pay attention. I don't want to be the only one feeling like I'm contributing to the class. All right. This is on page 35, or 34, I'm sorry. All right, we always calculate the p-value by assuming the null hypothesis as our starting point. As such, we build a model by sampling distribution that assumes a true null hypothesis. Then we test our sample to see how likely or unlikely our sample would be if the null were true. Here's an example. Let's assume that the water bill in Denver has been less than $55 per month for many years with standard deviation of 8, but a new water conservation program created to reduce the water bill. We plan to collect a random sample of 100 current water bills as evidence. The hypothesis is as follows. So they're saying we have a hypothesis, and they're using mu, which is fine. It's 55, and an alternative, which is less than 55. Okay, the average water bill is still 55. The average water bill is now below 55. All right, so we can create a null hypothesis sampling distribution. We know we plan to use a sample size of 100. 100's good. Mean and standard distribution would be 55 and 80 respectively, and then build our sampling distribution. So do you guys have a sampling distribution there, or do you have a big blank on your page? Okay. I just know that some of these pages have kind of gotten dorked up. So we have a mean of 55 and a standard deviation of 80. So basically, you have 55 here. This would be 5580. This should be 5660. And then over on this way, we have 5420. And subtract 5340. So there's basically our thing. If the null hypothesis is true, we would expect to see relatively close to the mean of 55. If we see an unlikely result, it calls for our null hypothesis in the question. As such, we use our result of our sample to weigh the evidence against the null. Simply put, the farther our sample is from the mean, the stronger evidence against the null. Okay, so let's say we create a sample of 100 people, and we find that the average cost is this. Okay, so 54.50. So we're somewhere in here. Okay, so that red dot down there, means if we come across something, we know right now I have the mean and standard deviations. So we have 54.50 sitting there. So we are within one standard deviation of the mean, which means we're within, that region is within 34% of our data. That seems okay. Okay, so let's see. This is a result that's very close to the mean on the bell curve. The sample would simply be a product of dumb luck. This sample doesn't provide much evidence against the null. Then let's say we have a sample of, let's say we do $45.75. So this value is like way down here on our normal curve. Our normal curve kept going. Okay, this is way below our normal curve, and it's very hard to believe the null could have possibly be true when the chance of producing the result is so low. Do you guys have anything underneath that paragraph? It says what? It ends with nope. Mikey, do you have anything down?
No, there's like a few paragraphs.
Yeah.
What does it say? You on page 35? Or 34, down there at the bottom. You have that. What does that say? It says
Let's
let's.
go to another example, but since we're still writing this and have this small amount of paper at the bottom of the page, we'll
Oh.
finish this.
Okay. I thought it was something important that I didn't have. Thank you. All right. Okay. Assume the political candidate is running for office, wants to have more than 50% support. We conduct a random sample of 400 likely. Thank you very much. Perfect. So we want the candidate to have more than 50% support. We'll conduct a random sample of 400 voters to see whether the candidate has this level of support. So our hypothesis is P is equal to 0.50, and our null is P is greater than 50%, so it's one tail, so we want bigger. It might seem strange to select 50% as a null hypothesis, but this value is our default baseline. Another acceptable option is that we have a null hypothesis less than 0.50. So we create the null hypothesis of 50%, standard error of 0.025, sketch the distribution. All right, so we say this is 0.5, and I gotta use calculator because I am, I don't want that calculator, I want this one. Clear. So they tell us we have a mean of this and a standard error, which is the same thing as standard deviation, of 0.025. So 0.5 plus 0.025, 0.525 plus 0.025. So that's 0.55. The opposite way, we go 0.5 minus 0.025, 0.475 minus 0.025, it's 0.45. Cool. All right, so our random sample that we first suggest is 52.7. So 52.7% is probably somewhere in here. Okay. So there's not really strong evidence against our null because we're saying that's equal. So the result is too close to the mean. Yes and no. I mean, they're saying it is. Our random sample, so then if we did a random sample of 57.2, this is really obscure based on this. So 52.7 is pretty close here, but 57, we're going to be way out here. So our random, this is far from our mean and is strong evidence against the null hypothesis. So we're going to finally start converting the p-value. We will be able to reject or fail to reject the null hypothesis based on this p-value. And just a couple of things that we've done. So we have the standard error equation. You have 1, which is this, and then we have 1, which is this. And we have to kind of go back and remember a few things. So n is the sample size. That's the same on both. This is going to be the standard deviation. And then over here on this one, this is the probability something will happen. Okay, and it goes into both. So an example of this one right here would be, let's say we had a standard deviation of 0.7 and we had a sample size of 300. So your standard error is going to be 0.7 over the square root of 300. And this is just a hypothetical. This is not something that's in your... So this would give me a 0.04 standard error. But then this would be if we were to say we have 30% that do something and we have a sample size of 200 people. So if we were to plug this in on this side, this would be a 0.30. 1 minus 0.30 is 0.70 over 200, and that's all under the square root. 0.3 times 0.7. Put that in parentheses. Forget I was using the calculator. It's going to be goofy. 0.3 times 0.37, 0.7 divided by 200. So in this case, this would come out to something like 0.03. So that's just a couple of examples that you might see as you progress along in this. Okay. So 6.6. I think if you attempted just page 103, I think you should be good with this. You might struggle a little bit with it, but that's okay. We'll go over it tomorrow. Sound good? Save.